welcome back. So this is post-lesson video 2, alright? We're just going to recap what we saw last week, in this last week's lesson. Overall orders of reaction, we have learned 0, 1 and 2. So we have this very pretty table for you. Make sure you take out that same piece of paper from last week, okay? Take it out and you're going to copy this table down, alright? Okay, so in this reaction, we're going to take a very, very simple reaction. A simply becomes P, and we have 3 orders of reaction here, 0, 1 and 2. Now we have the corresponding rate equations as well. Rate equals to A power 0, A power 1, A power 2. This should be quite comfortable for you now. And again, let's find out units of K. Right? Can you take that paper that you took out? Can you just remind yourself how do we find the units of K? We would use this generic formula here, right? This generic equation to find the units of K. Okay, so we're going to take that and we're going to use it right here. Let's go. Okay, so take note, if x plus y, which is the overall order, which is 0, then Mr. Leong, the units become?
So you tell me that you're going to apply x plus y to be 0, right? So just replace it, becomes 0. You notice that it's just simply the numerator. So mol dm minus 3 seconds inverse.
Okay, go on, Mr. Leong.
What happens if it's 1? Okay. So if the denominator here, the power is 1, then you notice that mol per dm cube is going to cancel. You're only going to left with seconds inverse.
Easy.
Alright? And finally, if it's power 2, you realize that there's more mol per dm cube in the denominator by power 1, and that's why you end up with mol inverse dm3 seconds inverse. Okay. So once again, when we talk about time, right, we do not always just assume that it's seconds. Sometimes, depending on the question, it could be minutes, it could be hours as well. So pay attention to the units for time as well.
Yes, very important. All right.
Now, moving on, we're going to take a look at the rate concentration graph. Now, when I say concentration, I'm referring to concentration of the reactant A. So I'm going to take a slightly more mathematical approach where I'm going to say that rate is going to be the y-axis, concentration of A will be the x-axis. And that, to draw the graph, the easy way is to always look at the rate equation. Okay, so I don't want you to memorize this. I want you to think of this in a mathematical way. If I take a look at the rate equation, I'll replace the rate with y. I'll replace the concentration of A with x. And you notice that for the first equation, y equals to k times of x power 0. Mr. Tim, what's x power 0?
1, right?
1, that's right. So you end up with just y equals to k. What kind of graph are you going to see?
Y, straight line.
Yes, it's a straight line, but you have to be more descriptive. What kind of straight line is this? Is it upward sloping, downward sloping, horizontal, vertical?
It's a horizontal straight line.
Yes, that's right. Can you draw for me a horizontal line?
Of course, sure
and
thing.
of course, the value of the horizontal line would just be k itself, the rate constant. Now, use the same approach. Let's take a look at what happens if you're having overall first order. You tell me that if you write rate equals to y, A equals to x, you're going to end up with y equals to kx. And what kind of graph is this now? Mr. Tim, bear in mind that you have to be descriptive in your words.
Yes. This reminds me of y equals to mx plus c, right? Easy stuff, but c is 0. So again, it is going to be an upward sloping straight line cutting through the origin.
Wow, very descriptive. So knowing that k is a positive value, it must always be upward sloping. That's right. And finally, if I take a look at overall order 2, if I were to replace it in terms of x and y, you are going to end up with this y equals to kx squared. And everybody knows that this is a quadratic graph. Mr. Tim, can you draw a quadratic for me?
Sure.
So this quadratic graph must pass through the origin, but obviously nobody is interested in negative a values. We're only interested in the positive. Therefore, I'm only looking out for the right-hand side of the graph, and this will be the shape of the graph.
Alright, now, for concentration time graph, I'm going to simplify this. It is quite simple. So just remind me first, Mr. Leong, for concentration of reactants, right, does it increase with time or decrease with time?
So like we mentioned last week, reactant must always be used up. It must be a decreasing graph.
Okay, so here's the thing. For a 0 order reaction, right, you just tell yourself it will be a downward sloping straight line that looks like this, okay? For order 1 and order 2, it will still be downward sloping, but it's no longer a straight line. They will be curves, right? So it will just be a curve,
Nice. Now, one very special thing about the first order downward sloping curve for a concentration time graph, right, is the fact that they have this thing called a constant half-life. Mr. Tim, what's a half-life?
Oh, half-life. Well, as the name implies, it is the time. So listen, guys, it is the time required for the concentration of the reactants to decrease by half. So 100% to 50%. And this time is T half. Yep.
That's right. So let's take a look at how it's being represented graphically.
Sure.
So we're going to start off with A naught, as you can see in the middle graph over here. And we're going to see how long it takes for A naught to drop to half of A naught. So Mr. Tim, can you draw for me half A naught? And then we're going to dot it down to give me the first half-life.
All right.
Now, the special thing about first order is that the half-lives are always constant. And to prove that to you, I'm going to go on to do the second half-life, right? So from from half of A naught, I'm going to halve it further. So now it's going to be 1/4 of A naught And let's take a look at the time that it needs to achieve that particular concentration. So you notice that this is going to be the second half-life. Now, the special thing about first order is that these two half-lives must be equal, or that's what we call a constant half-life. Okay, Mr. Tim, can you share with me some formulas on how to find out T half for a first order reaction?
Sure. So because the T half is constant, right, then your T half, very simply put, is just easily ln 2 over K. Okay.
Okay.
All right. Where K is just
the rate constant of the rate equation, right? So we are looking out for the equation at the top.
Yep.
There's another formula as well. So if I want to find out how many half-lives have elapsed, right? How do you find that?
Oh, simple. So basically, you tell yourself it is the fraction of A remaining, which means it's basically A, how much A or reagent that you have remaining, over the initial amount of A that you have, T equals to 0. This is equivalent to the fraction half raised to the power of the number of half-lives that has passed or elapsed, which is basically N. All right? Now, Mr. Leong, it's quite hard to remember this formula, right?
Okay.
So tell me which number is bigger, 1 or 2?
1.
Not quite. 2 is bigger than 1.
Oh,
right?
yes. Yeah,
so because of that, you tell yourself the initial amount, just like how 2 is bigger than 1, the initial amount must be more or must be bigger than the final amount remaining. Lovely.
Okay. Now, this kind of formula very prone to careless mistakes. First of which is the fact that people always think that the fraction on the left must be for products. No, you must always pay attention. It must be for the reactants. That's why the number in the numerator must be smaller than the denominator. The second one that is very common is people usually you don't pay attention to remaining. Right? So therefore, the other way to think of it is the left-hand side, right, of the formula is essentially the fraction of A left at some point of time. Okay, it's about the fraction or the proportion. Great. Now, Mr. Tim, can I throw you a question over here?
Go ahead.
For first order reactions, we are looking at half-lives, right? Does that mean that only first order reactions have half-lives? Other orders got half-life or not?
Well, that sounds so fishy. Of course there is half-life, right?
Okay.
Of course.
Right.
So if you look at the zero order, I'll do the same thing. Definition of half-life, the time taken for the initial amount of A, which is 100% in this case, to drop to half, which is 50%, right? Or half A, up to you. So 50%. This is your first half-life, all right? And if I do the same, 25% the second half-life now, from 50% to the second half-life, 25%. This is the second half-life. The first half-life was here. So you can see this, right, Mr. Leong? Is your half-life constant?
Probably not. It looks like it's decreasing.
Yeah, it's decreasing with time, okay? What about the second one? We can do the same thing, right? So again, start initial amount to half the initial amount. So in this case, it's A. I'm going to go half A.
Yes. So I think the whole idea over here is we're trying to emphasize that actually only first order half-lives, they are constant. Other than that, the rest of them are different, right? They are not going to be the same. It's just not constant. Okay?
Yep. So you can see how for the second order, the half-life actually increases with time. So it's not constant. All right?
So this graph very nicely summarizes for you the 3 different orders that you must learn for A levels, and as well as the different kinds of graphs that you must know, right? And obviously we are never encouraging you to memorize this. The whole idea over here is really to understand, and then after that you have to replicate it on your own as well.
Yes.
Okay. Now, one of the questions that we'll be having is this. So far we've been doing reactions that are very simple. A become P. There's only just one reactant. What happens if there's more than one reactant? As you can see over here, A plus B give me C. And let's say I've done experiments to come up with the rate equation. It's given by this over here. So one of the things I'm asking you here is this, Mr. Tim. Do you think I can use the T half equals to ln 2 over K formula to find out a half-life of this particular reaction?
Naughty boy, trying to trick me. You can't.
Right.
Because your overall order here, is it 1?
1 is for A, right?
Yeah. Your overall order here is actually 1 plus M.
Because we're looking for overall order, not just the order for A, right?
Exactly. And because your overall order is not 1, you cannot use your half-life formula.
But
no
I
way.
insist, Lei, I really want to use it. Can you tell me a way to do that?
Rebellious. Can. If you want, we can. Then we need to make sure that the concentration of all the other reagents must be held fixed. So let me repeat that. If you want to find a half-life for A, you better make sure the concentrations of all the other reagents is kept constant with time, okay? And how do I do that, Mr. Leong?
Hopefully, I think maybe I pray that B is actually a catalyst. But I think in this case, it doesn't look like a catalyst, right?
No.
It looks like a reactant. I hope there was a catalyst because catalysts are usually regenerated at the end of the reaction, which means that usually the concentration must be held constant throughout the entire reaction.
Okay.
But sadly, it's not, right?
No.
So maybe if it's a reactant, hopefully maybe the reactant is in severe large excess. That is good because you tell me that even though the reaction has progressed, the concentration of B remains relatively constant. So I hope that fulfills your criteria.
Yeah, it does. So when we mean large excess, we also mean that the concentration of B must be how many times more of A?
I mean, this is a rule of thumb, hopefully around at least 10 times, I would say.
At least 10 times of A, thereabout, right? So if that's the case, then you can tell yourself that B is now held constant, the concentration of B. So what we're going to do now is this. We're going to make it look like first order. So pseudo, make it look like first order, right? Since B is now constant, I'm going to group my constants together and I'm going to rebrand this. Let me just put this one side. I'm going to rebrand this as K prime A. And can you see how, Mr. Leong, it looks like overall order now is just 1.
Oh,
Lovely, good.
yes. Oh,
so
fantastic.
what's my half-life?
Wait, what's K prime first?
Oh, yeah. So remember, because how we brought B into the K, your K prime now is equals to K times B raised to the power of M.
Oh, so you actually combine all the constants together.
Yes,
okay,
correct.
sure. So I'm very happy. Now that overall order is 1, I can finally use my T half equals to ln 2 over K, right? Let's do that.
Wait. Ln 2 over K?
Yeah?
Or K prime?
Not K, meh?
K prime, right? Because now your new rate constant is now K prime, not K.
Okay, because I still need to use it for the overall order, first order, right?
Yes.
So I must use K prime.
Yes.
Okay.
So expand it a little bit more. So you can see now how the half-life is actually dependent on the concentration of B. Interesting stuff.
So this is called a pseudo first order reaction.
Good.
That's nice. So last lesson, we looked at a specific question type where the information that they give me is all in the table form, and my objective has always been finding out the order of a reaction. So this week, we're going to look at another question type, also same objective to always find out the order of reaction, but now the information are given in a graph. So there are two types of graph over here. Either you look at a reactant time graph or a product time graph. Let's look at the first one. For example, if I give you this reaction itself, propanone reacts with bromine to give me some random products, and H plus is written on top of the arrow. There's an indication that it is a catalyst. Okay. Now, we want to find out the order with respect to propanone as well as H plus. And we're going to see how we're going to do that. So, Mr. Tim, can you remind me, right?
Sure.
If, let's say I want to find out the order with respect to propanone, what must I do first?
Well, you need to make sure that every single other reagent or species is kept constant, right? The concentration.
Right. And of course, I mean, obviously the conditions must also be the same. The temperature must be constant as well. So this question was quite kind to me because they told me that bromine was also kept constant. So all I need to do is to make sure that H plus is also constant as well.
Okay.
So what we'll do is, if we look at the graph, this is a graph of propanone concentration against time. Right? And how do we make sure that H plus is constant? We simply just look at one graph. So for example, if I look at the blue color graph, the concentration is kept constant at 0.08 throughout the reaction. And why is that okay, Mr. Tim? How come the H plus concentration is so easily maintained at 0.08 throughout? Shouldn't it also decrease like other reactants?
Well, recall your definition of what a catalyst is, because H plus is a catalyst, right? It can be easily regenerated, right? It can be reused in a reaction. The concentration of catalyst does not change with time. Remember?
Nice. Okay, so it makes my life a lot easier, right? I just have to look at one graph, and turns out we're going to look at step 1. Whenever we do this kind of graphs, we're going to focus only on one graph. Doesn't matter which one you choose, red or blue also can. The first step is to see the shape of the graph, right? Now, if the graph was a downward sloping straight line, Mr. Tim, what order do you think that will be?
Downward sloping straight, zero order.
Yes, that's exactly what we discussed just now, right? From the table on top. But this is obviously not a straight line. This is going to be a curve. So I need to suspect perhaps it's going to be first or second order, right? And how do I prove that it's going to be a first order graph?
Well, we need to check the half-life, because if it's the first order, then your half-life is constant.
Sure. So what we're going to do is we're going to draw in the half-lives. So we're going to start off with 0.4 mole per dm cube, and we're going to half them. So we're going to look at 0.02 and look at the T half accordingly. And from there, Mr. Tim, roughly around 2.4, 2.8 minutes, right, thereabouts. Then we're going to go for a second one. So for this kind of question, you must always prove to me at least 2 half-lives. Obviously, when I say at least 2, it means 2 is sufficient. So you go for the second one, make sure that the second half-life is roughly the same. I know that sometimes because the graph, it might be inaccurate, you might get not very similar values, but as long as it's roughly the same, we can say that approximately constant, we can assume that the reaction is going to be first order with respect to propanone. Okay. Now, sometimes the questions are extremely nasty to you, right? They might truncate your graph in a very awkward position. So my point over here is that your half-lives do not need to be continuous. It doesn't need to be 0.4, 0.2, 0.1. In fact, if you want, you can do 0.4 to 0.2.
Yep.
And you can also do 0.3 to 0.15.
No problem.
The t-half will always be the same.
Yep.
If you don't believe me, you can try it on your own. Okay, so that is going to be the first step. Now I found out the order with respect to propanone. Mr. Tim, can you run me through how do you find out the order with respect to H plus then?
Sure thing. Now, if you want to find the order with respect to H plus, again, you need to make sure all the other species involved is kept constant. Okay. So if I want to see how H plus affects my rate, I need to keep propanone fixed. There's only one point where they are fixed, which is the initial time. Time equals to 0. Okay. So I want you guys to recall your tabular method, the table method, right? And we're going to do inspection, okay? So when the concentration of H plus increases by a factor of 1.5, so
1.6.
Excuse me, 1.6, not math 3, 1.6, okay? But I want to see how that affects my rate. But like I said, because you need to make sure the concentration of propanone is fixed, we're going to find the rate at t equals to 0, and that means initial rate. So I'm going to draw two gradients here, both t equals to 0 for the blue graph and for the red graph, all right? And please take note, your tangents, please try to make sure you cut the x-intercept or the x-axis so that when you find gradient, it's easier for you. You can just read off easily, right? Now, when you find these gradients, you tell yourself, as the concentration of H multiplies by 1.6, how did the concentration of the how did the gradients of your tangent change? Did it change by a factor of 1.6 power 0, or 1.6 power 1, or 1.6 power 2? Now, Mr. Leong, say if the gradient changed by 1.6 power 1, what do you think the order is?
It'll be first order with respect to H plus.
Yes, and that's it, okay? So this is how we find the order with respect to H plus. Keep propanone constant and see how the concentration affects the initial rate of reaction.
That's right. Now, last one small thing. Do you think you can find the order with respect to BR2? You say the answer is probably going to be a no, because if you look at the question, constantly your BR2 is being, it doesn't change, right, with time.
Yep.
So therefore, you tell me that at the end of the day, you are not going to be able to find the order with respect to BR2. We need more information for that to happen. Okay. Now, we've looked at reactant time graph, right? Shall we move on to product time graph now?
Sure.
So if you go on to the next question that we saw in our notes, one of the things that's very important over here is you must understand that the approach is slightly going to be a bit different, okay? Now, whenever I give you a product time graph, the clue is very straightforward. It is an upward sloping graph. And one of the things that you must pay attention to is to see when the reaction ends. So when I look at this graph, Mr. Tim, at time t equals to 120, right? Can I see that the reaction is complete?
No, because the gradient is not 0 yet, and the graph is not flat.
Okay.
If it's not flat, then the reaction is still progressing, right?
Yes. So one of the things that we want to do over here is to find out, hey, when the reaction is complete, how much of the product is being produced. So that is usually going to be step 1 of our product time graph analysis. So on the left hand side, you can see we have to find out the amount of products produced at the end of a day, and the only way to do that is to use stoichiometry, which means that you have to use you have to find out the number of moles of the reactants and use the chemical equation to help me to find out the final number of moles of the product.
Yep.
Okay. What about the step 2? We say that we have to take a look at the shape of the graph again. Now, Mr. Tim, if it's a upward sloping straight line, what order is that going to be?
Again, upward sloping straight line for product, that should be 0 order.
Oh, okay.
Yeah.
But most of the time, it doesn't happen all the time.
No,
I mean, you actually see this as a curve that looks like this, right?
Yep.
So we're going to see it's probably going to be a first or a second order, right? Now, if it's first order, I'll once again need to prove that it's a constant half-life. Mr. Tim, can you run me through how to do constant half-life?
Yeah, sure. Now, you got to be careful here, guys. You cannot just go 0% to half to 1/4. That's not right. That only applies for reactant, okay? So how do we find half-life for product? Now, here's the thing. You're going to take reference to reactant. So go through this with me. For the first half-life for a reactant time graph, you will tell yourself the first half-life for reactant, 100% to 50%. So for the product, it will also be 0% to 50%, because you're going to add it back, right? If the reactant decreased by 50%, the products increased by 50%. Now, if you look at the reactant, the next half-life, you'll be divided by 2, so 50% to 25%, right? This decreased by 25%, So for your product, it must increase by
25%,
25%.
to end up with 75%.
Good, very good. All right, and the last half-life here for the reactant, 25%, decrease by half again, 12.5%. This decreased by 12.5%, so your product must increase yet again by another 12.5%. Okay, but and then this is where the problem comes in. When I start to do my half-life on my product time curve, 50% of what value, Mr. Leong? I'm so confused.
So 50% must always be with respect to the final amount of products. And this is the reason why I asked you to do step 1 first, right? Find out what is the find out what's the final amount of products that you have, so you can find it's 50%.
Okay, so in this case, you guys can do the math on your own. The final number of moles of product, 100%, is actually 0.012. Okay, just take note. So 50% here, you'll be actually 50% of 0.012, which is 0.006. So the first half-life, do this with me, from 0% or 0 to 0.006, this is your first half-life. Okay, and the second half-life, again, you'll be from 50% of 0.012 or 0.012 to 75% of 0.012, which is, Mr. Leong?
0.009.
So this is now your second half-life, and does this look like it is constant, Mr. Leong?
Obviously, you're going to read the numbers, but it feels like it is going to be a constant half-life already.
Yeah, it looks like half-life is 50 seconds, right? And it's kind of fixed, which means the order with respect to I minus in this case, it is 1. Now, here's the thing, Mr. Leong, does it make sense to talk about why am I even talking about the order of reaction for a product? It doesn't make sense, right?
Nope.
No, it does not. So, in this case, please take this down. The order of reaction for a product actually refers to the order of reaction of the
limiting reactant.
Yes, that's incredibly important. So remind yourself this. If the order of reaction with respect to I minus is 1, this means nothing to you because we don't care about products. This means that actually the order of reaction of the limiting reagent in this question, which is 1-iodo-1-methylcyclohexane, C7H13.
The thing with the I lah.
Yeah, with the I, okay? The order of this reaction with respect to the thing with the I is 1, okay? And that's what it means.
That's right. Nice. So once again, let me just bring you through some of the pitfalls of the kind of mistakes that students make, right? Number 1 is that people don't really realize that the reaction is not complete. Then if they want to find out what is the half of the initial amount, half of the final amount, or 3/4, right? They take that to be the final value. They take this 0.01 to be the final value. So that's not okay. And number 2, people really like to take half and then not 3/4, you go for 1/4 because you mistook it to be a reactant time graph. So you can never go downwards for a product time graph. For product time graph, you're supposed to go upwards. So it's going to be half, 3/4, and 7/8. Okay, so nice. We have concluded the second question type, which is to look at graphs and then interpreting to find out what is the order of reaction. So that's it. Hope you have a good time. We'll see you in class soon. Bye-bye.